Today, I'll be introducing the concept of neuromorphic computing and discussing how Spintronic plays a critical role in enabling this innovative computing technology. Before we dive in the detail, let's take a step back and think about how traditional computer work and why we need something different to tackle the challenge of the future. So, traditional computers are built on what's called the von Neumann architecture. This means that the CPU, which is the brain of the computer, and the memory where the data is stored are separated. This separation allows the computer's functionality to be expanded more flexibly. But here is the problem. Moving data between the CPU and memory is slow and energy intensive. This creates something called the von Neumann bottleneck, which limits how fast and efficient computer can be. As more laws slow down, traditional computing methods face significant challenge in terms of performance and energy efficiency. We need a new way of thinking about how computer works, and that's where neuromorphic computing come in. What is neuromorphic computing? Neuromorphic computing is inspired by the human brain. Think about how your brain works. It's incredibly efficient, process information in parallel, and can store compute data in the same place. It mimics not only the brain neural network architecture, but also the function of neuron and synapses at the hardware level. Its key feature is first, it can combine computation and memory in one place, instead of separating them like traditional computers. Second, non-binary information processing. Unlike binary data, neuromorphic system process spike, which is short bursts of electrical signal. Third, high connectivity, similar to the massively parallel connection in biological neural network. And spintronic is a field of electronic that use the spin of electron, a quantum property, to store and process information, which make it perfect for neuromorphic computing. First, it is non-volatility. A device like magnetic tunnel junction (MTJ) can store information even when the power is off. This is crucial for mimicking the brain's long-term memory. Second, its energy efficiency. Spintronic device can operate at very low power, just like how the brain works. Third, scalability. Spintronic can be used to build large-scale neural network, enables systems that are both powerful and compact. And the last one is its versatility. Spintronic device can mimic neuron-like behaviors, such as oscillation and randomness, which are essential for brain-like computing. And here are some examples of spintronic in neuromorphic computing, such as spin-torque nano oscillator, spin-torque magnetic tunneling structure. And we will talk about them in the next few parts.
Okay, hello everyone. My name is Kwang Lon, and I will take the next part from my partner. Previously, my partner will introduce some briefly introduction for the computer learning. So, in my part, I will visualize it and show you how to the computer learning. before we go to figure out how computer learning, we can see in this video. So as you can see over here, this is the water bath, and they use the mice to training for the training. This is the water bath, and in the center of water bath, they have a platform. So the mice, if the mice would like to survive, the mice need to find out the way, the fastest way to come to the platform. And we can see they training the mice, how they training the mice. It's the initial state. The mice don't know how to reach the platform, so they try many way to reach, to learning the platform. And after the mice is well training, which means that the mice can recognize the platform very quickly, they make the platform become invisible, and even they remove the platform, the mice still can reach the platform very quickly. Even the platform is not over there, the mice still find out the way to come back to the platform. So it means that during the learning, there are some connection inside the mice brain, so it helps the mice reach the platform very quickly. So let's see how computer learning and can recognize something. In the artificial neuron, they use some mathematics model, and for example, is this image. They separate it to 784 unit, and each unit will have some value, and we call that value is the activation value. So each unit is like a neuron. It's like a neuron. So the activation, they separate into the array of neuron, and then they connect to the second layer. And we can see over here, each number, they have something very similar together. And you can see so they will separate the first layer to the second layer. In the second layer, after calculation, they recognize something, and after calculation, they will training the model how to recognize the number over here by calculation. And during the training, the thing make the neuron connect together, we call the weight, and each weight will hold different number, represent for the different strength of the connection. So during the learning, by calculate from the first layer to the second layer or the third layer, the system will find out the weight that is most fastly and have a lowest error to figure out the final question. So in the conventional GPU, this operation is will carry out in the parallel, and therefore its execution is very fast. However, in the computer training system, they have some very big challenge. The first one is the data during the training is not the analog, because in the biological synapse in our brains, the the information stored as the analog, while in the computer is the digital, so it cannot fully mimic the biological system. Another thing is very important is the high power consumption. As we know, the data in the computer can be stored in the binary system, and this information will store in the memory, the RAM. However, as we know during the class, the DRAM will require the continuous power to to maintain the memory, as well as during the update, during the training. So it will consume a lot of energies. Another thing is because the RAM and memory is separation, so the data must be moved between the memory and processor constantly. So it makes the power consumption much more higher. So to overcome this challenge, one research group in the National Yang Ming Chiao Tong University near our university will introduce the method to use the Spintronic device to mimic the neural synapse, neural computing. So I will present this paper to show you how the Spintronic device can mimic the biological system. And also because the time is limited, so with some information in this paper, I will not go very deeply. So this is the basic structure of the device in the paper. As we can see in the device, they construct the heavy metal layer, and on top the heavy metal layer, they have the ferromagnet layer, and on top the ferromagnet layer, they have anti-ferromagnet layer. So to make the device work, they use the current density along the x direction, inject into the heavy metal layer. So because of the Hall effect, the spin current in the heavy metal layer will inject into the ferromagnet layer and also move the domain wall inside the antiferromagnet layer. And because the domain wall in the antiferromagnet layer will move, they will generate different resistance state. And because of the different resistance state, we can mimic the synaptic weight. And for the training, to adjust the resistance state, they use the pulse and direction control to react the LTP and LTD. So after training, the electrical readout will allow user to take out the resistance inside the device to use in the neuromorphic system. And recall the neuron system in the biological is the neuron in the biological, and each neuron they will connect together by the synapse. So this synapse will represent for the strength connection between two neurons. And in this paper, by using by using different pulse amplitude from the minus to the positive, they can create several resistance state. And the several resistance state over here can mimic the synapse strength. So they use the different resistance state for as the analog information for the LTP and LTD during the training for the model. So we remember the previous video in the connection between the neuron, we call the weight. So by using this device, we create several resistance state, and several resistance state over here we can use for the connection between the neuron in the artificial neuron system, and they will utilize it for the training. And we can see over here the training accuracy is comparable with the ideal. This is the ideal training, and the the by using this device, they can reach the accuracy comparable with the ideal case. So the most after this paper, we can highlight why they use the Spintronic AFM SOT device. So because the SOT Spintronic device can physically represent for the synapse, so it can take the multiple resistant analog value. So it allows for more biological, realistic synaptic and plasticity. And we know that spintronic device is non-volatile and low power consumption. Therefore, the device it don't need the power to maintain the information. So it's only need the power during the training. So it will help us lower the power consumption in the training as well as using the device. So this is my part, and my partner will take the next presentation. Thank you.
My part is about artificial synapses and their realization in by spin orbit talk. First, I would like to discuss the requirements of the device to be used as artificial synapses. So, as our member just mentioned, artificial synapses uh, need to have good storage and plasticity. So to be a good memory, it needs to be non-volatile for better power efficiency and durable enough to handle lots of read and writes. Finally, if the memory use multi-level cells to store more than just 0 and 1, it can better imitate how our brain works. Since human thinking isn't as binary as traditional computers. Second is plasticity. The memory doesn't just store data. It needs to adjust its way to control how signals pass between neurons. One kind of learning based on Urban theory is called spike timing dependent plasticity, or STDP. Here, the weight changes depending on the timing between the presynaptic and postsynaptic spikes. And I will show more about this in the next slide. Okay, so in this slide, I'm going to show you how STDP is realized in a real spin orbit torque device. Here is an SOT device connect with 4 assessing transistors. There are 2 kinds of signals. The V spike is a transmission signal, and the V pre and V post are the programming signals. And the V spike travels to the post neuron, and at the same time, the pre-neuron applies V pre for learning. So what's important here is that V pre lasts for a time window, while V post is just a short pause used to sample the learning current from V pre. The next question is how LTP and LTD are achieved. As you guys may know, the LTP means the time of the post-neuron spike is later than the pre-neuron spike, and vice versa. The weight depends on the in this device, the weight is depends on the overlapping current. To realize the To realize the LTD, the V-pre is delayed, making it overlap with the precurrent. So the conductance variation with time corresponds with the STDP learning. Before we go deeper into the SOT device, I would like to show you the concept of multi-level. And here I take SSD NAND as an example. In the NAND structure, the storage unit cell is composed of floating gate transistors. By controlling the voltage, the number of electrons is categorized and represent bits. If the number of electrons is well controlled at a certain voltage window, the multi-level cell can be created and thus store more information in one cell. And now I'm going to introduce a multi-level SOT device. The device is composed of a multi-layer cobalt platinum structure, where the number of layers is n equals 1, 2, and 4. When n equals 1, the device shows a binary property, and when n equals to 4, the cell turns into demagnetized states. But when n equals 2, the device shows a current-dependent magnetization. So we further plot a contour of this magnetization state. So we can see only when n equals to 2, the multi-level structure can be seen from this figure. And now we are going to discuss why multi-level structure can be observed only when n equals to 2. So in this paper, the authors do another experiment. In this experiment, we applied a strong field to simulate the combined effect of SOT and the longitudinal field. And the result shows a tangent hyperbolic line curve. And from the curve fitting, we can extract the value of theta MD. So as n increases, the theta ND also increases, meaning the device becomes harder to fully magnetize. And also from the class, we know that as the number of layers increases, the magnetostatic energy also increases. So the formation of a multi-domain can lower the total energy. So this is the reason why the multi-level behavior is shown in this structure. Okay, finally, I will make a brief summary of my part. So in this device, an electric pulse generates SOT with the help of longitudinal magnetic field. The magnetization of cluster is tilted out of plane. After the external force are removed, the magnetization relaxes back toward the easy axis, eventually settling into a stable intermediate state. But when n equals 1, the multi-domain does not form, while in the case of n equals 4, the total magnetization is split into small domains, and the degree of randomness is so high that the demagnetized state forms. Only when suitable structure is introduced, the multi-level state are obtained in this device.
So now I'm going to introduce two components that is very important in the neuromorphic computing. The first one is the spin-hole nano oscillator. What is a spin-hole nano oscillator? We know that a magnetic moment will try to align with the external field to fulfill the lowest energy, and that is the kind of the thermodynamic effect because we want to get to the lowest energy. But what is the dynamic between the process? So this is the key driving force for the oscillation. And this process is described by the LLG equation. It describes the motion of the moments in the external field. So we have the left-hand side. We have the this m is the moment, and it is a vector, and derived with respect to t. So it is the change of the magnetization change direction. And we have the precession term here, and damping and the spin polarization. And I'm going to elaborate these three separately. So first we see the precession term here. It is determined by the moment and the external field. So as the figure shows, the moment is here and the magnetic field is here. And if we cross these two, we can get the vector that is this direction is the kind of the tangential direction. And what does this mean? The tangential torque here is going to pull the magnetic moment in a circular or the precession motion. So this is the origin of the oscillation, is the precession of the moment about the external field axis. So if only this term exists, then the moment will forever rotating around the external field. But we know that the moment have to finally align with the edge field. So there is the term in the material is the damping term. And this term is, we have the moment here, and we have partial m partial t, which is this. And if we ignore this damping term, then this partial m partial t is actually this tangential in this tangential direction. And if we cross this m and this partial m partial t, which is this, then we get a rate vector here. And this is the damping term. What this damping term do is the damping term will pull the magnetic moment toward the center. So these two together will define the motion of the moments inside field. So it will kind of behave like the spiraling motion, with the precession angle becomes smaller and smaller, and finally it will align with the edge, the field. So the oscillation only appear few moments, then you will finally, because of the damping, you align with the field. But what if we can come up with the term that cancel out the damping? Then the precession can go on forever. So this is where the spin Hall effect comes in. So we know that the spin Hall effect is when we inject a current into a heavy metal, then the current will, and we can get a pure spin current. So that is the term here, the polarization term. And when the polarization direction and the amplitude is just cancel out the damping term, then this oscillation is going to persist. Like the figure shows, when we put a structure like this, we can we can cross the M and the P. The M is the black arrow here, and the P is in the in-plane direction. If we cross these two, we get around the z-axis, and if we cross to M again, we can get a vector that is this green green torque here. So it's about just cancel out this term. So if the spin polarization term cancel out this damping term, then there is only the precession term going on. So the oscillator is going to oscillate until the polarization is gone. And this oscillation produce a microwave frequency and produce a microwave signal. So this is the spin Hall nano oscillator. And the next one I'm going to introduce is the memristor. And this is the combination of two words, the memory and the resistor. So this is the resistor that can have memory. So this is the classic configuration. We have the pure TiO2 here, which is insulating, and the doped TiO2 with oxygen vacancy. I will use the little plus sign to represent. So when we have these two, the insulating TiO2 and the conductive TiO2 junction together, and if we apply a voltage like this, we have the positive here, negative here, then the oxygen vacancy will diffuse into the insulating layer, and this insulating layer will become more conductive than before. So overall, the resistance will be lower because of the drifting of the oxygen vacancy. And if we reverse the bias like this, then the oxygen vacancy will diffuse back to a conductive layer. So this will make the insulating layer recover its resistance. So this is the high resistance state. And both of these two states are non-volatile. So if you stop the voltage, then they will stay their state, their low or high resistance state. So what is the relation between spin Hall nano oscillator, MEM resistor, and the synapse? As for the oscillator, we know that only when the polarization cancel out the damping term will the oscillator begin to oscillate. So this damping term is act as a threshold. So when the polarization reach the threshold, these two cancel out each other, then the precession will start. So this is very similar in synapse. So the synapses have to be stimulated to its threshold level to emit a spike signal. So like this one, it did not reach the threshold, so there's no activation. And this stimulation accumulates to the threshold, so there's a spike happening here. So this kind of threshold behavior is very similar in this oscillator, because when we exceed the threshold, the oscillation will start. And for the memristor, this can act as the weight system in a synaptic. The synaptic strength will increase when you reuse this route very often. Like the figure shows, the receiver become more, so the sensitivity is is larger, so the synaptic strength is increased and the connection is enhanced. And we can, for the memristor, we actually can see this as a low resistance state. And this with fewer transmitter, we can deem it as a high resistance state. And these are non-volatile. And in a memory system, we can always switch between these two. And that is also true for the neuron. So that's my introduction of these two key components. And to make a device that utilize these two components, we're going to discuss the paper that do the device of these two components. And I'll hand it over to my partner.
Okay, so I'm Chen Yanci. So, and now I'm going to introduce a paper about the memory-resistive control of the spin-hole nano-oscillator for the neuromorphic computing. And this paper is published in Nature Materials. Okay, so for the partner, they introduced that the spin-hole nano-oscillator is a room temperature gigahertz auto oscillator that can mutually synchronize. And for the memory resistor, this is for the non-volatile and multi-level resistance. So this is like a perfect local weight storage. So for the the memory resistor is likely synapse, and the SHNO is like an artificial neuron. So here is the device overview of the memristor and the SHNO. So we can see that the SHNO is cut into the tungsten and a cobalt iron boron and a manganese oxide strip. So when a DC current flows, the spin hole effects in the tungsten will produce a spin current into the ferromagnetic and will make the auto oscillation of the microwave. And on the top side, we can see that here is the main resistor of the titanium and the copper top gate. Okay, so and we can see that between the SHNO and the main resistor, there is a silicon SINX, silicon nitrogen, which is for the conducting ions of the path of the conducting ions. Okay, so stacking one main resistor on every SHNO is like giving each artificial neuron to its own permanent synapse. So we can see that in figure A and figure B, there's two states. For the figure A is for the high resistance state. And how to generate the high resistance state is that we use the electric field only, which is called a VCMA mode. So there are few electric field across the insulating stack will change the PMA of the cobalt iron boron. And another part is for the low resistance state, which is called LRS. That is when we snap the gate into a low resistance current, and we can see that there are some currents between the main resistor and the SHNO in the SINX. Okay, so there is some microampere bias will add it and will give a instantaneous frequency drop, and we will see that in the next page. So first, I will talk about the one memory resistive control with one SHNO. So in figure A, there's a SEM image of this device, and we can see that M is for the memristor, and the bottom part is for the SHNO. Okay, so we can see that this figure is for the frequency versus the VM, and VM is for the memristor voltage. Okay, so we can see that with adding the memristor voltage up, we will see that the frequency will be synchronized. That is, there will be one frequency, and the frequency will drop a little bit. And after the memristor frequency added to the 4V, and we'll call it V set. And we can see that the device changed from the HRS into the LRS, and we can see that there's a frequency abrupt jumps into the into the device. Okay, so as we can see, in the LRS states, they will have an extra 100 microampere joins the bias current. Okay, so another part is for the figure B is that when we do the reverse sweeps of the memristor voltage, we can see that when we drops the voltage from 4 to about 0 minus 0.2 volts, and the device will change from LRS into the HRS once again, and we will see that the current will vanish. And so next part is for the two SHNOs with two memristors. Okay, so we can see that here is the SEM image of the SEM image of the device. We can see that there's two SHNO with two N1 and 2 memristor. Okay, so we can see that in figure A, when we add the current of the SHNO, we can see that the frequency will change, will synchronize with only one line. Okay, so with no gate bias, the two neighboring oscillators will be one clean peak. Okay, we will see that there are no splits on the frequency. Okay, so the next part is we will add the positive bias of the memristor 1. Okay, so when we add up the voltage, we can see that the frequency first as the minus region, the negative region, you can see that there's split on the frequency. We call it F1 and F2. But after we add the voltage up, we can see that the frequency will synchronize. That is, the frequency will combine together into one clean peak. Okay, so moreover, when we add up the voltage into V sets around like 2.1 V, we can see that the state of the device will turn from HRS into the LRS state. That means the current will added like about 100 microampere. Okay, so we can see that there is a jump of the frequency. Okay, so we can see that driving the gate into the low state will pump the extra current. So we will widen the gap beyond the locking range. Okay. So, and it is same for the reverse sweeps of the voltage. We can see that there is the same scenario in the previous page I mentioned. Okay, so after talking about two experiments, then this is the third experiment they introduce, is that now they use 4 SHNOs with 2 memristors. And for the SEM image, we can see that here is the SHNO 1, 2, 3, 4, and here are 2 memristors combined with each other. And first, I will mention that it is the VCMA control, and that is we use only electric field. That is use the electric field of the main resistor. We only use the main resistor gate to control the voltage. Okay, so we can see that when we add up the currents of the SHNO, then the frequency will split from one path into 2 paths around like 0.712 MA. And we will say that 2 paths will for the frequency SHNO 1 and 2 and frequency of SHNO 3 and 4. Okay, so for oscillator starts as 2 pairs, each pair on its own note. And we can see that in figure BCG is for the forward sweeps of the it's for the one scenario of the device, and EFG is for the another scenario of the device. Okay, and BCG is talking about sweeping the memristor of the first memristor of the voltage, and EFG is sweeping the second memristor of the voltage. Okay, so we can see that when we add up the voltage of the N1, so the frequency of the 3 and 4 SHNO will drop down and will be synchronized into one clear path. And also for the reverse sweeps, we can see the same scenario. And and another part, when we sweep the second memristor of the voltage of the memristor, and we can see that there's another scenario for the frequency, and we can see that they're split into the 3+1 situation of the frequency. Okay. So we can see that in this part we will have the 3 combination of the frequency, that is 3+1 or 2+2 or the 4 groups synchrony. Okay, so the previous part is for the electric field control, that is VCMA control, and another part is for the memristor control, that is we change the flipping the main current and the magnetic field, and we can see that the muting edge and the ISHNO is turned from positive sign into the negative sign. And we can see that when we add up the ISHNO, and we can see that there cannot pull the 2 pairs together. That means there's just only frequency 1 and 2 and frequency 3 and 4 for the 2 pairs of SHNO. Okay, so for the figure BCE, there's the same explanation for the SHNO and the memristor. Okay, so when we sweeping the memristor voltage, we can see that there's a frequency 3 and 4 drops and will be synchronized. And also for the reverse sweeps, we can see the same situation. So so after introducing like four experiments of the memristor plus the SHNO, and here the paper will mention an idea about the phase lock password. That is so we can see that in the figure A, there we can imagine a 6-chain of the SHNO with 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 a memristor on the top, and so we will program the 6 gates with a set of the small resistance. So only when we replay the exact and the precise same voltage will added the current up and the frequency will be generate the strong microwave peak. Okay, so any mismatch will leave the weaker tone output. So this like will act as an analog hardware key for the pattern recognition and the security. So for this device outlook, we can see that there are 4 points. The first one is the scales, naturally. So we can see that the memristor gates can be placed on any oscillator. So that is, we can read and write the memory and have a good combination with each other. And the second is for the parts is that they will stay ultra low power. And we can see that when we're tuning the electric field or the current, we can see that there's only micro scales in a microwave frequency range. So we can have the low power. And the third one is for the edge device friendly. So this oscillator network will be attractive for the edge hardware. So we can memory and read and storage the memory on the same chip. Okay, so the last part is for a clear growth path. Okay, so earlier demonstration of this two-dimensional SHNO and the spin hole materials will be pointed out to the ultra low power neuromorphic computation. And that's for the all presentation. Thank you.